Okay, in this video we're going to take a look at another related rate problems, this time with shadows and angles. So let's get right into it. The angle of elevation of the sun is decreasing at a rate of 0.25 radians per hour. How fast is the shadow cast by a 400-foot tall building increasing when the angle of elevation of the sun is pi over 6? Alright, now that we've read the problem, our first key step in solving it is to find any rates of change and express those as derivatives. So for example, at the very beginning of the problem, this one says that the angle of elevation is decreasing at a rate of 0.25 radians per hour. Now, the units themselves tell you that that is a rate of change, and we can express this as the change in theta, the change in the angle, over a change in time, is equal to negative, because it's decreasing, 0.25 radians per hour. Okay, now there's no other units like that in this problem, like something per hour or something per second, but the question itself is always a derivative in these related rate problems. So how fast the shadow is increasing, we can express that as ds, the change in the shadow's length, over dt, is equal to question mark. So that's what we're looking for. So those are all the rates of change either told about in this problem or asked about in this problem. And again, that's the first key step in solving a related rate problem. Okay, our second key step in solving a related rate problem is to find an expression that relates together the variables which are changing in the problem. So in this case, the angle theta and the length s of the shadow. Now, when we're dealing with angles, a lot of times the best strategy to do this is to draw a picture. So here we have a 400-foot tall building. We have the sun up in the sky, and the sun's rays hit the top of the building and cast a shadow along the ground. Now, the length of the shadow, it's changing as the sun sets. We'll call this S, okay? And the angle that that shadow makes with the sun, we'll call that the angle of elevation, and we're going to call that theta. All right, so now we need some type of trig function that relates together these things given in this problem. So the angle theta, now the height of the building is across from that, or the opposite side, and the length of the shadow is adjacent to that, or right next to it. So the trig function that has opposites and adjacents in it is tangent. So namely, we have tangent of theta is equal to the opposite side, 400, over the adjacent side, s. Okay, so now this is an expression that deals together with the angle theta and the length of the shadow, s. But we can simplify this a little bit, and it'll make our lives a little bit easier when we do our next step of taking the derivative. Namely, since I'm trying to figure out ds dt, it would be nice if s was by itself and not in the denominator of a fraction. So I can do this by just cross multiplying, and we'll get s times tangent of theta is equal to 400. And then to avoid a product rule, I'll divide both sides by tangent. We get s is equal to 400 over tangent. And the nice thing about having tangent in the denominator is that it just turns into the reciprocal of tangent, which is just another trig function. And we know that that is cotangent. Okay, so there is a relationship between the length of the shadow s and the angle theta of elevation. Okay. All right, our final key step in solving a related rate problem is to take our derivative with respect to time using implicit differentiation and chain rules as they come across. So we're going to take the derivative of the entire expression with respect to time. So the derivative s, again, is just 1, but then anytime you take the derivative of any variable in a related rate problem, we need to tack on d variable dt, so in this case, ds dt. Okay, so that's why I put s by itself. So now it's just already solved for ds dt, and that's what we're looking for. Okay, now the derivative of the other side, the 400 just sits there, and the derivative of cotangent is negative cosecant squared of theta. And then again, we need to tack on our little chain rule here. The derivative of theta is d theta dt. Okay, our final step here is just to plug in the given information and solve for what it's asking for. So in this case, it's asking for ds dt, and we're already solved for ds dt. And we're just going to plug in the given information. So 400 times negative cosecant squared of the angle is pi over 6. Okay. And then the d theta dt is the negative 0.25 radians per hour that we plugged in at the beginning. Okay. All right, so now we could do this in the calculator. We could use a unit circle, but it's just arithmetic at this point, really. So we have 400 times negative, and then cosecant squared of pi over 6, if we threw that into, say, sine, so it's 1 over sine squared of pi over 6, to help us think about it, or to use the calculator, times negative 0.25. Okay, so we'll have 400, and then negative 1 over, and sine of pi over 6, we could use our calculator, unit circle, that's 1/2. So we're going to get 1/2 squared, and then times another negative 0.25 over here. Okay, and now we could use our calculator to do all this, and if we multiply all this stuff out, it's just going to come out to be 400. Okay, now we can look at the derivative itself to think about the units. So ds is a change in the shadow's length, and in this problem, length was measured in feet. Okay, and dt was a unit of time, and time in this problem was radians per hour, so time is hours. So the length of the shadow is increasing at 400 feet per hour at this time.